Unit 1, Looking Inside the Black Box Video Review. You can find this review, as well as the video, at srhschem.wikispaces.com and on YouTube at channel LEFFELlabs. The first problem is regarding Rutherford's gold foil experiment. For each of the following, explain what Rutherford determined about the atom. Most of the alpha particles flew through the foil. So here we can see our alpha particle emitter is firing alpha particles at the gold foil. And we see that most of the alpha particles are flying straight through, but there's that one alpha particle that is deflecting. Let's go ahead and zoom in on one of these gold foil atoms. So we're going to go zoom in on a single atom, and we see that we have our nucleus in the middle with 2 electrons orbiting. And if I'm firing alpha particles at this particular gold atom, we see that the alpha particles usually go through, but if one of those alpha particles gets close to the nucleus, we see deflection. Rutherford found that the vast majority of particles pass straight through the foil, but approximately 1 in 8,000 were deflected. In order for the alpha particles to pass through the atom must be empty space, with nothing to block the path of the alpha particles. Some of the alpha particles bounced back. So once again, we can take a close-up view of our gold atom, and we see that the reason this alpha particle is bouncing away is because it is coming in contact with that nucleus. About 1 in 8,000 of the positive alpha particles were deflected. In order for them to bounce back, they would have to ricochet off something very dense and very heavy. This object would also have to be positive in order to deflect positive alpha particles, because light charges repel. Later, this dense positive object in the center of the atom became known as the nucleus, made of protons and neutrons. How are these results inconsistent with the plum pudding model of the atom? So here we have Thomson's plum pudding model. It is a sphere of positive charge with electrons embedded in. It's called plum pudding because this was a dessert, kind of like oatmeal with raisins mixed in. The oatmeal would be the sphere of positive charge, that's green on your screen, and the raisins mixed in the oatmeal would be the electrons. Those are the small blue dots on the screen. If I fire alpha particles at this atom, all of the alpha particles are going to fly straight through. The plum pudding model is just a sphere of positive empty space with electrons mixed in. All of the alpha particles would have gone through if plum pudding was the correct model of the atom. But instead, Rutherford saw some of those particles bounce back. Therefore, he knew that plum pudding could not be the correct model of the atom. So the reason this is consistent is because all of the particles are going through 100% of the time. In the actual experiment, Rutherford saw that about 1 in 8,000 alpha particles actually bounced back. How should the plum pudding model of the atom be changed to reflect this evidence? Well, first, you need to add a dense positive nucleus. This explains why some of the alpha particles bounced back. The rest of the atom needs to be empty space. This is why most of the alpha particles flew straight through. Next question is about subatomic particles. So subatomic, sub means below. So subatomic particles are particles that are smaller than atoms. They're the things that make up atoms. So protons are found in the nucleus and they have a positive charge. Neutrons are also found in the nucleus, and they are neutral. And electrons are found orbiting the nucleus, and they are negative. So here they are represented by the 2 electrons flying around on the screen. Next question is about isotopes. So for the first letter, letter A, we have a hydrogen. Now the top number is the mass number. The bottom number is the atomic number. The way we write the name of the element, you put the element name, a dash, and then the mass number. So for cobalt-59, that 59 is the mass number. Remember, the atomic number is the same thing as the number of protons, and you can remember this with AP, atomic number, number of protons. The mass number is the sum of protons and neutrons. A good way to remember that is because most of the mass of the atom is in the nucleus, which is protons and neutrons. And to find the charge, you simply take protons minus electrons. Keep in mind that protons are positive and electrons are negative, so depending on how these balance out, that's what charge we end up with. So for our first letter A, this is hydrogen 3. I know it's hydrogen because that is the name that corresponds with the symbol H, and I know that 3 is there because the top number, the mass number, is 3. Hydrogen is atomic number 1. I can figure that out by looking at the table of elements. I find hydrogen and I look at the number on top, and that tells me that the atomic number is 1, which is also the same thing as the number of protons. My mass number is 3. I was given that, which means that I must have 2 neutrons. The mass number is the sum of protons and neutrons. So if I have 1 proton and my mass number is 3, I must have 2 neutrons. The charge is 0, therefore I must have 1 electron. So for the charge to be 0, I would have to have 1 minus 1 to get 0. Protons minus electrons. Letter B has cobalt-59. So I can look at my table of elements. I see that the atomic number for cobalt is 27, which means that I also have 27 protons. My mass number is 59. We were given that. So in order to find the number of neutrons, I need to take my mass number and subtract my protons. Again, mass number is protons plus neutrons. So if I have 59 for my mass number and 27 of those 59 are protons, that must mean that the rest, 32, is going to be neutrons. The charge on this atom is minus 1, which means that I must have 1 more electron than proton. So if I do 27 minus 28, I get negative 1, which is the correct charge. Now to write the symbol. The symbol for cobalt is Co. The bottom number is the atomic number, 27, and the top number is the mass number, 59. For letter C, the atomic number is 1, which tells me right away that this has 1 proton. The mass number is also 1. The mass number is protons plus neutrons. So if my mass number is 1 and I have 1 proton, that must mean that I have no neutrons. The charge is going to be plus 1. If I do protons minus electrons, that's 1 minus 0. That is positive 1. I can look at my table of elements and see that atomic number corresponds to hydrogen. The 1 in the name of the element comes from the mass number. So when I write my symbol, the symbol for hydrogen is H. I have 1 proton, so my atomic number on bottom is 1, and my mass number is also 1. For letter D, the atomic number is 27, therefore I know I have 27 protons. The mass number is the sum of protons and neutrons. So if I add 66 plus 27, protons and neutrons, I get a mass number of 93. The charge of this particular atom is plus 1. That means that I must have 1 more proton than electron. So if I do 27 minus 26, that leaves me with positive 1. So I can look this up on the table of elements, and I see that atomic number 27 corresponds to cobalt. The 93 is the mass number, protons plus neutrons. And to write the symbol for cobalt is Co. The atomic number is still 27. That's always true for cobalt. If it didn't have 27 protons, it wouldn't be cobalt. It would be something else. And 93 is the mass number, so that goes on top. Letter E. So I've got 28 protons, which means that my atomic number is 28. To figure out neutrons, Mass number is protons plus neutrons. So my mass number is 62. 28 out of those 62 is going to be protons, so that means that 34 must be neutrons, because 28 and 34, when you add them together, make 62. I have 2 more electrons than protons. So if I do 28 minus 30, protons minus electrons, I get -2. This particular element is nickel. I know that because nickel corresponds to atomic number 28, and the mass number is 62. The symbol for nickel is Ni. 28 goes on bottom, that is the atomic number, and 62 goes on top, that is the mass number. So in the table, which letters represent isotopes? So isotopes are atoms of the same element. In other words, they have the same number of protons, but they have different number of neutrons. Another way to say this is that the atomic number is the same, because the atomic number is just the number of protons, but the mass number is different. Again, mass number is protons plus neutrons, so if I have a different number of neutrons, that's going to affect my mass number. So the isotopes here are going to be A and C, and B and D. If you look at A and C, you see that the symbol is hydrogen for both. You also see that the number on bottom is 1 for both. That's how I know that I have the same element. The number on top, the 3 and the 1, those numbers are different because these two isotopes have different numbers of neutrons. Same thing for cobalt. I see that CO is the same for both B and D. 27 is the same for both B and D, but the number on top, the mass number, is different. So a quick way to tell if you have isotopes, just look at the protons and the neutrons. Protons should be the same, but neutrons should be different. Which represent cations. So a cation is a positively charged particles. So if you look at the charge, you see that C and D have a positive charge. Therefore, they are cations. Anions are negatively charged particles. So that's going to be B and E. They both have a negative charge. So in an isotope, the number of protons or atomic number is always the same, and this is because protons equals the atomic number, but the number of neutrons or mass number varies. Both are correct because mass number is protons plus neutrons. So if I have a different number of neutrons, it's going to affect my mass number. Why are different colors of light given off during a flame test? So, during a flame test, energy is supplied to electrons from the heat of the flame. The electrons absorb this energy. So here's my electron traveling in the first energy level, and it's going to absorb energy. So there's my energy, the electron absorbs it. Now the electron is going to jump up in energy level. So it jumped up to energy level 3. This is very unstable. We call this the excited state. In order to jump back down, to fall back down, the electron needs to release energy. This returns the electron to the stable ground state. While falling down, this energy can be released as light. And if it's just the right amount of light, we can see it with our eyes. Sometimes it might be infrared or ultraviolet, which our eyes can't see. But if it's the right amount of energy, our eyes are able to see it. And the amount of energy, so how far the electron jumped down, determines what color we will see. Number 7 asks about which elements are found in the mixture below. So this is a bright line spectra for lithium, cadmium, and strontium. The bright line spectra is like the fingerprint of light that the atom gives off. So the best way to do this, you need to get a ruler, and you need to take the ruler and you need to line it up with the mixture. So every place where I see a line that matches up with the mixture, I'm going to highlight them both. So here we see that these two lines match. We're going to continue this all the way across, so we got a match there, a match there. So as you're doing this, you should just pull your ruler, making sure, following along with mixture, and highlight everything that matches one of the mixture lines. And sometimes when the lines are close together, this can be a little bit tricky. So we see these guys line up here, these guys line up. And this doesn't quite line up with cadmium. It's very close, but it does line up with strontium. So let's see, this next line matches up here and here. And then these last two So we see that for lithium, I have all of the lines highlighted. For cadmium, I'm missing some of the lines. I do have one of them highlighted, but that's just because it happened to line up with one of the lines in the mixture. That also lines up with the line in lithium. And then for strontium, I also have all of the lines highlighted. Because the bright spectral lines for lithium and strontium match the mixture, these two elements must be present in the mixture. If cadmium was present, then I would see more lines that would correspond to where cadmium absorbs light. Next question asks, how do I use the number of protons to determine the identity of an element? So, the number of protons is the atomic number. So you just find the atomic number on the table of elements. So if I have 8 protons, that means the atomic number is 8, and that matches up to oxygen. I need to measure out 10 milliliters of a liquid. Which should I use? So obviously we're not going to use the ruler. That's silly. The decision comes down to a beaker or a graduated cylinder. What we're going to use is the graduated cylinder. They are more accurate than a beaker. So for a graduated cylinder, somebody checked to make sure that the volume of these was accurate. For the beaker, a machine just stamped those lines on there. Nobody checked to make sure that what said 50 milliliters on the beaker is actually there. Next question is to convert each of the following. So, there are 3 conversion factors that you need to know to do these problems. The way that you do these problems, you start out with the number that you are given. So I've got 56.36 liters, and you always need to include a unit. I'm going to put a 1 on bottom. This is just a placeholder. Now this next line is for my conversion factor. I'm trying to get rid of liters, which means that liters needs to be on bottom, because if I divide liters by liters, it cancels out to 1. I want to get milliliters, so that needs to go on top. So when I look at my conversion factor, I see that 1 liter is 1,000 milliliters. So to solve this problem, I just need to multiply my answer by 1,000. So if I do 56.56 times 1,000, it's going to give me 56,360 milliliters. Next question asks us to convert grams to kilograms. So again, start with the number that you are given. Don't forget your unit. I'm going to start by putting this over 1. This next line is for my conversion factor. I'm trying to get rid of grams, so it needs to go on bottom because grams divided by grams is 1. And I want kilograms, so that needs to go on top. So my conversion factor says that 1 kilogram is 1,000 grams. So to solve this, I just take my starting number and divide by 1,000. So when I do that, 15,689 becomes 15.689. And my units here are kilograms. Last problem asks us to convert 200 centimeters to meters. Now you might look at this problem and know right away that it's 2 meters because 100 centimeters is a meter. But let's set this up the correct way. If you get in the habit of doing it this way, whenever you get more challenging problems, it would be more automatic. So I'm going to start with the number I'm given, 200 centimeters, and I'm going to put it over 1. This next line is for my conversion factor. I'm trying to get rid of centimeters and change it to meters. 1 meter is 100 centimeters. So 200 divided by 100 is simply 2 meters. Next problem asks us to calculate the average atomic mass of bromine. So, what I recommend you do with these problems, start them off by highlighting all of the information about one isotope. So that's the first isotope. There's its relative abundance. The other major isotope has an atomic mass of 80.92 AMU and a relative abundance of 49.31. Okay, so I already have set up here our table. A good way to remember this is I passed, that's for percent abundance, I is for isotope. I passed Denny's, which is for decimal. Atomic mass starts with AT, so I passed Denny's at, and mass is midnight. So, I've got 2 isotopes here. The problem tells me I have 2. So the first isotope has a percent abundance of 50.69. The second isotope has a percent abundance of 49.31. Now I need to take these 2 numbers and write them as a decimal. In order to do that, I divide by 100. Now I need to find the atomic mass. So for the first isotope, the atomic mass is 78.92. And for the second isotope, it's 80.92. To get the last column, I need to multiply the decimal by the atomic mass. What this does is it finds the mass taking into account the fact that it's not a 50-50 split. It's a little bit uneven. My last step is to take these numbers and add them up. And I get 79.9062, and my units are AMU. I know this because my atomic mass in the problem was also given in AMU. Last thing that you need to do, find bromine, or whatever the atom is, on the table of elements, and check the number on bottom. So this number down here, that is the average atomic mass of bromine. That's what you just calculated. So if we compare, we see that our numbers are very close. I'm only off by 0.2, so that tells me that I did this problem correctly. What are the signs of a chemical reaction? So we could have a color change. So something could go from clear into a color, or it could become cloudy. We could have the formation of a solid. That's what causes something to become cloudy, because we have insoluble solid in the solution. There could be a change in temperature, so something could warm up or cool down. A formation of a gas, so we would see bubbles. Decomposition is another one. So that would be like a piece of wood rotting. That's a chemical reaction. We could have light, energy, or heat, or all of them given off. So in the case of something like an explosion, we hear the explosion, we feel heat from the explosion, and we see the light from the explosion. So those are all signs of a chemical reaction. Last question asks us to provide an example of the law of conservation of mass. So, law of conservation of mass is why chemistry is even possible. It's why you don't disappear 1 minute to the next. It says that during any chemical or physical change, mass is conserved. In other words, the mass of everything I started with will be equal to the mass of everything after. And this works for a closed system. So let me show you an example. I have a piece of wood, and I'm going to put it into a closed container. So now this is a closed system. Nothing can get in or out. And inside of this is 10 grams of wood and oxygen. If I completely burn all of the wood, what I'm going to be left with is ash, water vapor, and carbon dioxide. The mass of what I started with was 10 grams. The mass of what I end with will be 10 grams. Now, if this container wasn't on top of my wood whenever I burned it, the carbon dioxide and the water vapor would escape because they're gases. So if I didn't have this glass cube, it would look like matter wasn't conserved, even though it was. The problem would have been that my carbon dioxide and water vapor escaped, so I couldn't weigh them at the end of this. So, some tips for test taking. You should complete your review. Circle any questions that you do not understand the first time going through, and then ask about them. Make flashcards for tricky topics only. If you make them for everything, that's a waste of time. Only make them for the things that you seem to struggle with. A good way to figure out which topics you're struggling with is to look over previous quizzes. Check to see which questions you got correct and find answers to the ones you got wrong. The night before, take about 30 minutes to go over your review and make sure you get a good night's sleep. And in the morning, of course, eat breakfast. You can find this on srhschem.wikispaces.com. You can also find this on my YouTube channel, LEFFELlabs.